Hi, Year 10. We've been talking about speed and acceleration and things, and now we're going to look at how you make something accelerate. And no surprises, you can see from the heading here, you're going to need to use a force. Either you are going to need to push it, or you're going to need something else to push it, an engine, a motor, whatever. So let's get started. Firstly, you can probably figure this out yourselves. This is one of the most famous laws in physics, but you can probably work it out just by thinking about it. If you look at that diagram there, I've got two cars which are exactly the same, and I'm going to push one with a big force, big F, big arrow, and one with a small force, small f, small arrow. Which one's going to accelerate the most? Well, of course, the one with the biggest arrow, right? It's probably quite logical to you that the acceleration will be bigger when the force is bigger. And mathematically, we write this like that, as in acceleration is directly proportional to the force, right? So in other words, you double the force, you double the acceleration. I'm pretty sure you will have seen this relationship in maths at some point. Okay, so let's have a look at another situation. This time I'm using the same force on both cars, but one of them is bigger than the other. Now which one's going to accelerate the most? Well, hopefully you realise that the little car should accelerate more for the same force. A bigger car, a bigger mass, is going to need more force to give you the same acceleration. That means that when we're thinking about the mass of the car, when it's the mass of the car that's changing, the bigger the mass, the smaller the acceleration. We call that inversely proportional. And what we write is acceleration is proportional to 1 over mass. It just means that when one gets bigger, the other gets smaller. I'm actually going to write that little sign a bit better there. It's that sign. Do you recognise that? It's the Greek letter alpha, and we use it to mean proportional, or in this case, inversely proportional, because we're going to put it upside down like that. Now, this is famously known in physics as Newton's second law. We'll have a look at Newton's first law later on, but we're going to do the second law first. And it's a way that describes the relationship, it's a law that describes the relationship between the force, the mass and the acceleration. Let's have a look. It comes out to look like this. It's called Newton's second law, and I'm just going to put on here what we measure these things in. We measure force in newtons. I think you might have known that. And do you know why? Because of Isaac Newton, of course. Mass is always in kilograms. We must get the mass into kilograms for this equation to work. And the acceleration, we now know, is in meters per second squared. Yeah. Now we can write other versions of that. I could rearrange it to make it m equals f over a, which we don't use very often. Or we could make it a equals f over m. And that we do use quite a lot because it's quite useful to be able to calculate how much acceleration you should get for a certain force and a certain mass. Okay, what we're going to do is practice using this. But before we do that, I'm just going to show you, for those of you who are keen on maths, I'm just going to show you how this links to what we already said. Okay, so if you don't want to, if you're not worried about the maths, or if maths scares you, terrifies you, skip the next 30 seconds. Okay, so for those of you who are interested in maths, it actually comes from, we're going to look at this bit here. We said on the previous two slides, we said acceleration is proportional to the force. And we also said acceleration is proportional to 1 over the mass. In other words, it's inversely proportional to the mass. And when we put those together, we would get this. Now in our equation, we've changed it to an equal sign, and we can do that if we have the force in newtons, the mass in kilograms, and the acceleration in meters per second squared. If you're going to go using some strange units of force, like the Americans do, they use dynes and strange things like that, then you're going to need something else to go in here before you can make it in equals. But provided we are using newtons, kilograms and meters per second squared, we directly change that to an equals and everything works perfectly. Okay, those who were panicking about the maths, you can come back now. All right, here we go, let's practice. So I'm just going to put at the top here, again, my 3 versions of the equation. If you want to make a note of these, it's probably a good idea to do that so that you don't have to keep flicking back in the video to see the different versions of it. What did we have? That was the 3 versions, wasn't it? Okay, so this in this question, what force is needed to accelerate a box of mass 6 kilograms at 3 meters per second squared? We're going to find the force, so we're going to use this version of the equation. And all we need to do is substitute in the numbers. So our mass is 6 kilograms, our acceleration is 3 meters per second squared, and 6 times 3 is 18. So our force is going to be 18 newtons. Yep, that's all there is to it. You might not even need a calculator. In this one, if a force of 10 newtons pulls a crate of 5 kilograms along the floor, what will be the acceleration? So if we're going to work out acceleration, we want this version of the equation. We know that the force is 10, and hopefully you can spot that that 5 kilograms mentioned there is the mass. If it's kilograms, it's mass. So 10 over 5, that will give me 2 meters per second squared. If you don't like rearranging equations, remember the first one. Put your numbers in first, and then sometimes it's easier to rearrange. So for example, I could do here F equals ma, substitute in my force is 10, my mass is 5, 10 equals 5 times a. Well, then it becomes a little bit easier to spot without doing a rearrange. Yeah. It doesn't matter which one of those methods you use, they're both great. All right. Here's the last version. We worked out a force, then we worked out an acceleration, now we're going to work out a mass. So we've got a toy car accelerating at 3 meters per second squared when a force of 1.5 newtons acts on it. What's the mass of the car? So if I want to do it using the rearranged version, it's going to be that one. So let's do it this way first. So my force is 1.5. My acceleration is 3, and that's going to give me 0.5 meter, oops, no, not meters per second squared. I'm working out a mass, aren't I? 0.5 kilograms. Yep. Or if you want to do it by substituting in instead of rearranging, your force 1.5, your mass is what we're trying to find, and it's times by 3. And again, you might be able to spot quite easy there that the mass is going to be 0.5 kilograms. Okay. Remember, of course, you're allowed to use your calculators, but do be careful when you divide that you divide the right way around. Remember that 1.5 divided by 3 is not the same as 3 divided by 1.5. It's quite a common mistake to make when we're doing calculator work in physics, that. So if you got an answer there of 2 kilograms, you're wrong, and that's why you're wrong. You divided the wrong way around. Okay. Sometimes we've got more than one force acting. So I don't know if you can actually see the numbers on here, but this is labelled as a car with a mass of 800 kilograms. And here we've got an engine force of 1,500 newtons. And we've got a frictional force of 500 newtons. I think that says, yeah. So the frictional force, or any force that slows the car down, is going to act against it. Yeah. And what we need to do is to work out the balance of these forces. we work out something that's called a resultant force. So if we've got 1,500 newtons pushing one way, but 500 newtons pushing back the other way, hopefully you can tell what the resultant force is going to be, what the balance of this is going to be. It's going to be 1,000 newtons. Yeah. We call this the resultant force. Sometimes you will also hear it called an unbalanced force. I suppose what that means is that 500 newtons of the original 1,500 was balanced out by the 500 newtons friction, and the 1,000 newtons is what's left, not balanced. Okay, so if we were going to work out the acceleration here, we're going to do force over mass, and we're going to take the resultant force. We're going to take the 1,000 and we're going to divide that by the 800. And I think that will give me 1.25. I realised I've started to do this video without having a calculator anywhere near me, so I might have to pause and go and get one. So 1.25 meters per second squared. Yep. So you are going to practice today doing some calculations using this equation, the Newton's second law equation, in its 3 different versions. But you're also going to calculate doing some balancing forces like this, looking at a diagram where you've got more than one force acting and figuring out what is the resultant force. So here's an example. Right, in this 3 examples actually. In the first one, we've got a 10 Newton force and we've got a 20 Newton force. And if you look at the arrows, they are both pushing towards the right. They're both pushing from left to right. So our resultant, they're acting in the same direction. So our resultant is going to be 30 newtons, 10 plus 20, acted in the same direction. Yep. In the next one, we've got 40 newtons pushing from left to right, but we've got 20 newtons pushing in the other direction. Yep. So our resultant is going to be the difference of those. It's going to be 40 minus 20. And it's going to be in that direction, isn't it? It's going to be in the direction of the biggest force. In the last one, we've got 25 newtons pushing one way and 25 newtons pushing the other way. So these ones are going to exactly cancel. And we'll have 0 newtons. 0. There's a fancy term for this in physics, which says it's in equilibrium. It means there's no unbalanced forces acting. And what you should spot straight away is 0 newtons means I'm going to get 0 acceleration, and therefore this thing is going to have a constant speed. It's not going to be changing its speed. All right. Here are some examples now where we're going to put 2 equations together. You'll see here we haven't been given an acceleration. We've been given some information about speed and time that will allow us to calculate an acceleration. So this is revising what we did last week. All right, so let's try it. Part A says, what's the acceleration of the car? Remember, the acceleration of the car was the change in speed, which we sometimes show as that as a shorthand, that delta triangle sign. I think I showed you that last week, didn't I? It's a short way of writing change. So there's change in velocity or change in speed divided by the time. So my change in velocity here is 20 minus 12, and I'm going to divide it by 4. So that's 8 over 4, which is 2 meters per second squared. And then in B, the resultant force. Well, now we've got the acceleration, we can use that along with the mass that they give us in the question to work out the force. So here we're going to do the F equals ma bit. And it's 2,000 for the mass and it's 2 for the acceleration, so that is 4,000 newtons. Yeah. So you're going to get some practice today at using the equation that you learned last week as well. Here's a car that hasn't been drawn yet, so I'm going to draw you a car here. Don't laugh at my cars. Okay, you will get to know I'm not very good at drawing. Right, this car has 2 forces acting on it. Its engine force is acting, oops, engines with an N, not an M. Engine force, which we don't know, and there's a frictional or air resistance force. Let's say that is 1,200 newtons. And this car is moving at a constant speed of 15 meters per second. We're going to work out what the engine force is. A good term here, if you want a short way of saying friction and air resistance or any other force that's slowing the car down, you can call it drag force or drag forces. They're the forces that act against you. Okay. Can you see a clue in here to tell us what the acceleration is? Whenever you see constant speed, you know that the acceleration is 0, and therefore the total force must be 0. So constant speed always tells you that the forces are balanced. Let's say balanced forces. And that tells you, of course, that the engine force must be exactly the same as the drag forces, so that we end up with 0 altogether. So you need to look for clues like this in questions sometimes. There's nothing in this question that tells us specifically that acceleration is 0. There's nothing in this question that tells us specifically that the forces are balanced. So we have to be able to pick up clues like this about constant speed to figure that out. Constant speed means 0 acceleration, therefore balanced forces. You'll notice that the 15 meters per second there doesn't matter at all. If it's a constant speed, it doesn't matter whether it's 15 meters per second or 150 meters per second or 0.02 meters per second. If it's a constant speed, it's a constant speed and there's no acceleration. Okay? Right. What I would like you to do now is to try this sheet. This is just the start of it. I've added it to Classroom as well. Have a go at this sheet. And then when you've practiced all of those questions, you're going to do an experiment. So come back and watch the second video once you've had a go at this sheet.